Hello everyone. In this video, we're going to look at the physical design and timing in a DE1 SoC board. So we just open the Quartus Prime, and if you are doing this for the first time, you need to create a new project and give the name as DE1 SoC underscore IR. Since I've already done, I'm just going on and opening the project which is already created. So as we can see, as I already created the project, I already have the files here. So if you're creating a new project, once you're created the project, you need to right click on the files and give add or remove project files. And then you need to choose all the .v and .sdc files that you have and just give add all and give OK. So once you're done, you can see all the files here. We need to set this as the top level entity, and I'm going to compile the design. So we need to wait till everything gets compiled. As you can see, the design is fully compiled, and we can see the flow summary here. So the number of ALMs is 183, the total number of registers is 284, and we have 241 pins here, and the number of DSP blocks and DLLs is 0. So once we are done with this, we are going to go to timing analyzer, and we are going to first see the maximum frequency of this design. So you're going to give report fmax summary. So as we can see, the maximum frequency of uh, is 166.67 megahertz. And once we are done, we just move on to report timing. Here we are going to report 5 paths. So we give the number of paths as 5, and we get hit report timing, and we get the report. So for 5, we have total of 5 paths, and the slack ranges from 14 nanoseconds to 14.010, and we have a delay of 5.748, somewhere between 5.738 and 5.748. So this is the delay and this is the slack. Now we are going to do one thing. We are going to alter the uh, clock settings in the SDC file, and we are going to see what uh, slack, how does that is going to affect the slack and the delay. For that, we need to close this timing analyzer, go back to the Quartus. We need to open the .sdc file, and instead of 50, we are going to give 500, and the time period we are going to change it as 2 nanoseconds. And we are going to open the timing analyzer and check what difference we get. We are going to save this, and we need to compile the design once again to make the changes effective. So we need to wait till the design is compiled. We can see that the design is compiled fully, and there is no change in the flow summary. So we are going to go to the timing analyzer, when we are going to check what's has changed in the slack and the delay. So same 5 paths, git report timing. As we can see, there is a violation. So if you go on and change the clock, we do get a violation here. So once you're done, just close this window, go back and put back the clock to the old settings, which is 50 and 20 nanoseconds. And we are going to compile it once again, and we are going to proceed with the chip planner later. So we need to wait till the design is compiled. So the compilation is done. Uh, we move on to the timing analyzer. We go to report timing, same 5 paths. We are going to give report, and now we are going to change the register location in the chip planner. So we just go into the chip planner and we are going to zoom in where the critical path is. So here this is the critical path, and what we are going to do is we are going to choose one register randomly. So let's say from here I'm going to shift this one, uh, just go zoom in a bit. So I'm going to shift this register all the way to the bottom. Just choosing this, and so mm, so I randomly select this register and I'm going to drag it and connect it all the way down to the left end. Still in 47. Mm, as you can see, I'm connecting this all the way down here, and we go back to the same location, and we are going to connect one more to the top right. Maybe we can choose this, and we are going to connect this register all the way to the top of the FPGA. So I'm connecting it somewhere here. So once we are done with connecting it, it is saved, and we are going to close this window and close the timing analyzer too, and we have to compile it one more time for the placements to get updated. So we need to wait till the design is compiled. We can see that the compilation is done, and again we go to tools, we go to the timing analyzer, and now we are going to check at the report timing, and we are going to check at slack and the delay if something has changed. We go there and we give report timing. See, as we have increased the path, we have taken the register from one end to the other end of the FPGA. Obviously, the path has increased, therefore, the delay has also increased compared to the original case, and the slack has reduced. So this is the change that we can see when we move the register from one part to the another part. So once we are done, we can close this window. Next, we are going to uh, take this SOF file from the outputs, and we are going to paste it near the BAT file, and we are going to run and check the output if it works on the board.
So now we are going to look at how to configure the FPGA board using the batch file. So the first step is to go to the batch file, and this is the batch file that we are going to run. And once the board is run, and we need to cut the SOF file, and we have to paste it in the location where we have the bat file, and we need to right click the bat file, and we need to go into the editor, scroll all the way down, and we need to give the path of the SOF file here. We have to save it and close it. Once this is done, we need to right click, and we need to run this as administrator. We need to give run. So once we give this, we can see that it is running, and once this is successfully done, we can see this in the board.